the power of the lens is basically measured in diopters, or just P. Now the focal length of a lens is f, which is equal to 1/2 the radius of curvature that we talked about before, the center to the edge of the circle. Now the power is equal to 1 over f, so if you can keep that in mind, it'll be much easier to solve the thin lens equation, because P is equal to 1 over distance of the object plus the 1 over image of the object. So as you can see here, you'll notice that these lenses have a thicker center. There's this key term, if you remember it, it's called thicker centers means converging. So you can tell that these lenses here are going to converge the image because the center here is much thicker than, say, the top edges. So this edge here is very thin, but this center is much thicker. This edge at the very bottom is very thin. Same thing with this one here. You'll notice this is, this is much more tricky to understand, but this here is much thicker than, say, this end here. In real life, if you saw it, you'll notice it much more easily. Although it's much easier just to keep in mind, this is actually very similar to a convex, lens. It might as well be, because it pretty much just takes the convex shape and just takes the mirror shape of it exactly. Now this here is a double concave lens. How that would be implemented is this. Again, you look at the end. This is much thicker than the center, so it's the opposite. Now it's going to diverge the image. Same thing here. This piano concave lens, it must somehow diverge the image because the center isn't very thick, but the edges are. Same thing up here. The center isn't very thick, but this is actually much more complicated. This is, again, we're going back to concave mirrors. Just think of this, the negative minuscule lens, as the concave mirror, and as you know, the light will strike it, it'll come out, it'll diverge, but it'll have to make some kind of virtual image, because that's what a concave mirror does. The virtual image will be somewhere over here.